Let's talk about the 3D graphics transformation pipeline. Basically, how does a 3D model in your game engine or modeling software actually become flat and correctly positioned on your 2D screen? So let's start with the basic problem. You've modeled this beautiful 3D cube in Blender or Maya or whatever tool you are using. That cube exists in its own local coordinate system. We call this model space. The corner might be at coordinates like 0.5, 0.5, 0.5. Simple enough. But now you want to render that cube on your screen. Your screen is a 2D grid of pixels, so somehow we need to take those 3D coordinates and figure out which pixels they should map to. That's what this whole pipeline is about. And here's the thing, it's not just one transformation, it's actually a series of transformations, each one moving our vertices through different coordinate spaces. Each space serves a specific purpose in the rendering process. Before we jump into pipeline, we need to talk about homogeneous coordinates for a second. Instead of representing a 3D point as x, y, z, we actually use 4 components, x, y, z, w. Now, why would we do this? There are a few really clever reasons. First, it allows us to represent translation as a matrix multiplication instead of addition. Second, and that is the really cool part, it lets us implement perspective projection where distant objects appear smaller through a simple division operation. When w equals 1, we have a regular point. When w equals 0, we have a direction vector. And to convert back to 3D, we just divide. The actual coordinates are x/w, the same for y and z. Keep this in mind because it's going to be crucial when we get to the projection step. Alright, let's walk through the pipeline. Step 1. Model to world transformation. Your 3D object lives in its own local space. Maybe you model the character and the origin is at their feet, and they are facing along the positive z-axis. But in your game world, you want that character standing at a specific location, maybe rotated to face a different direction, perhaps scaled up or down. That's what the model matrix does. It's a 4x4 matrix that combines rotation, scaling, and translation. Looking at the example on screen, you can see the model matrix has rotation and scale information in the upper left 3x3 block and translation in the rightmost column. We are going to follow the path of this yellow vertex. When I keep the cube in its default location, you can see that the vertex is at 0.5, 0.5, 0.5, which is exactly how we modeled it. But when I move it around, watch the last column. Now we are defining its position in the world. One grid cell represents 0.5 times 0.5 meters. A vertex 2.5 meters away from the camera will have a z-coordinate of -2 in our model-to-view matrix. Because the vertex started at -0.5, we need to move it by 2 meters to reach 2.5. When we multiply our vertex by this matrix, it's now positioned in a world space where all objects in your scene exist together. Next step, world-to-view transformation. This is where the camera comes in. Everything in your world is positioned in this common coordinate system, but now we need to think about it from the camera's perspective. The view matrix transforms everything so that camera is at the origin, looking down the negative z-axis, in my case. This is often constructed using what's called a look-at matrix. You give it 3 things: where the camera is, the eye position, where it's looking at, the target, and which way is up. From these, the graphics system builds a transformation matrix. In our example, the view matrix is just an identity matrix, which means the camera happens to be at the origin already, looking down the negative z-axis. So our coordinates don't change in this step, but in a typical game or 3D application, this is where the camera's position and orientation get applied. Now here's where it gets really interesting. The projection transformation. This is the step that creates perspective. You know, that effect where train tracks appear to converge in the distance or distant mountains look smaller. It's also where we prepare for the transition from 3D to 2D. The projection matrix is pretty fascinating. Look at the bottom row, 0, 0, minus 1, 0. This is crucial. When we multiply our vertex by this matrix, that bottom row copies the negative z-coordinate into the w component. So if a point is at z equal -5, remember negative z is forward in view space, then w becomes 5. The matrix also scales our x and y coordinates based on the field of view. A wider field of view means less scaling, a narrower field of view means more scaling. That's how you get zoom effects. After this multiplication, we have what's called crib space coordinates. They are still in homogeneous form, and w is no longer necessarily 1. Next comes perspective division, and this is where the magic happens. We take our crib space coordinates and divide x, y, and z by w. So x equal x divided by w, and same for y and z. Remember how distant objects have larger w values? When we divide by a larger number, we get a smaller result. That's literally how perspective works in the math. A vertex at z minus 10 will have a bigger w than a vertex at z minus 2. So after dividing, its x and y coordinates will be proportionally smaller. It appears smaller on the screen. After this division, we are in what's called normalized device coordinate space, or NDC. This is a standardized coordinate system where visible points fall between -1 and 1 in all 3 dimensions. Anything outside that range gets clipped. It's not visible, so we don't bother rendering it. I don't have it written down here, so just imagine it. The final step is the viewport transformation. We take those normalized coordinates from -1 to 1 and map them to actual pixel coordinates on your screen. If your window is 1920 pixels wide, then x equal -1 maps to pixel 0, x equals 0 maps to pixel 960, and x plus 1 maps to pixel 1920. There's also usually a y-axis frame here because in NDC space, y increases upward, but in screen coordinates, y typically increases downward from the top of the screen. The z-coordinate gets remapped from -1 to 1 for the depth buffer, which is how the graphic system knows which objects are in front of others. Now, here's a really important optimization that you'll see in real graphics code. The MVP matrix. Instead of doing 3 separate matrix multiplications, model, then view, then projection, we can pre-multiply those matrices together into one combined matrix, MVP, P times V times M. And yes, order matters here. Matrix multiplication is not commutative. You have to multiply them in the correct order. Projection times view times model. Then you can transform each vertex with just one matrix vector multiplication. So the new point is actually MVP times point. This is way more efficient, especially when you are transforming thousands of millions of vertices every frame. You compute the MVP matrix once per object, then apply it to all the object's vertices. And there you have it, the complete 3D graphics transformation pipeline. We went from model space through world space and view space, into grip space with the projection, then perspective division gives us NDC space, and finally viewport transformation landed us at actual screen pixels. Every vertex in every 3D game, every 3D modeling viewport, every visualization you see, they all go through this exact pipeline. It's the fundamental process that makes 3D graphics possible on our 2D screens. I know there's a lot of math here, but the concepts are actually pretty elegant once you see how they all fit together. Each transformation has a specific job, and together they solve this really hard problem of projecting 3D geometry onto 2D display while preserving depth and perspective. If you want to dive deeper into any of these topics, maybe you want to understand how to derive the perspective projection metrics or how to construct different types of camera matrices, let me know in the comments. I'm thinking about doing some follow-up videos on specific aspects of this pipeline, so hit the subscribe button if you want to see more. Thanks for watching, and I'll see you in the next one.